In this video, we will practice working with polynomial functions. We'll be finding absolute and relative extrema, as well as points of inflection, etc. This is AP Precalculus Topic 1.4. If you appreciate this channel, please hit the like button. For each of the following, determine if the given function is a polynomial. If the function is a polynomial, indicate the degree. A polynomial is a function that can be written in this form, where a0, a1, a2, a3, and so on are called the coefficients. And these coefficients can be any real number. So a1 could be pi, a2 could be negative 2.3, a3 could be radical 7. These coefficients can be any real number. On the other hand, the variables and their exponents. The exponents can only be the natural numbers. I said natural numbers. They can only be the whole numbers, 0, 1, 2, 3, 4, and so on. This is x to the 0 power and x to the 1 power. They can't be anything else. They can't be fractions or negative numbers or anything like that. For example, problem number 1 is a polynomial, yes. You might notice that the term with degree 2 is missing. It goes straight from degree 1 to degree 3. That's okay. That just means that the coefficient of that particular term is 0, which is a real number. The degree of the polynomial is the degree of the leading coefficient, which is the highest exponent in the polynomial. So this polynomial has degree 4. Problem number 2 is not a polynomial because you can't have any exponents that are variables like this. Looking at problem number 3, this is not a polynomial because you can't have exponents that are negative. K of x is a polynomial because it does fit the pattern that I described below, and the degree is 5, the highest exponent. Number 5, p of x looks a little bit strange because we have a coefficient of pi and a coefficient of e, but yes, this is still a polynomial. E and pi are both real numbers. Pi is approximately 3.14 and e is approximately 2.72. These are real numbers. This is a polynomial. The degree is 3. It's the highest exponent, so the degree is 3. Notice that this is considered the leading term even though it's not written first. Number 6, m of x is a polynomial. Even though it is not written in standard form like this, you can imagine doing the distributive property and multiplying every term of the trinomial by 4, and then multiplying every term by negative 3x squared. We're not going to take the time to do that because we don't need to do that to answer the question, but if you did multiply that out, you would see the polynomial in standard form like this by focusing on the leading term of each factor. So in other words, I can find the leading term by multiplying negative 3x squared times x squared. That is going to give me negative 3x to the 4th power as the leading term of m of x. Therefore, the degree is 4. For each of the following polynomial graphs, determine any x values where the graph has a local extrema. If the graph does not have a specific local extrema, write none in the appropriate space. Local extrema, so that means local maxima or local minima. So we can see that we have 2 local minima. There's one at the bottom of this valley here and the one here, where the graph changes from decreasing to increasing. So that's at x equals 1 and x equals 6. We have one local maximum at x equals 3. That's where the graph changes from increasing to decreasing. It didn't happen on this particular problem, but watch out for problems that have a limited domain. if there were dots on the ends here, indicating that these graphs did not go on forever because we have a limited domain, then these two giant dots I just drew would be local maxima as well. Endpoints also count. It looks like number 8 has no local minimum. There is no place on the graph where the function goes from decreasing to increasing. It is increasing all the way up to here and then decreasing. So we're just going to say none for that. There is one local maximum right here where the graph changes from increasing to decreasing. That's at x equals 7. Number 9 has relative minima here, here, and here. This graph does have a limited domain, so the endpoints count when we talk about relative maxima or minima. So we have relative minima at x equals -1, 4, and 9. Similarly, we have relative maxima here, here, and here. That endpoint counts. So that's at x equals -2, +2, and 8. Number 10 has relative minima here and here. Close circle, this endpoint does count as a local minimum. So that's at x equals 2 and what is this? 1, 2, 3, 4, 5, 2 and 6. Notice this does not count as a relative minimum because the arrow tells us that this graph really keeps going. This graph has relative maxima here and here. So that's x equals -4 and +5. For number 11 and 12, the directions have changed a little bit. We are now being asked for the location and value of absolute extrema, sometimes called global extrema. So this graph has an absolute minimum right here. An absolute minimum is the lowest point on the entire graph. When you're asked what the minimum is, you give the y value. So this graph has an absolute minimum of 2 at x equals 6. The arrows on the end tell us that this graph keeps going up forever on both sides. So we would say that this graph has no absolute maximum. So we're just going to say none. Similarly, the arrows on this graph means that there is no absolute minimum. So we're going to say none again. There is an absolute maximum right here. This is the highest point on the graph, and the absolute maximum is 8 at x equals 7. Practicing our vocabulary, notice that global minimum and global maximum, that's the same thing as absolute minimum and absolute maximum. This graph has an absolute, or this time I'll say global minimum right here. This global minimum is 3 at x equals -1. The absolute highest point on this graph, including the endpoints, is right here. This maximum, this global maximum, is 8 at x equals, well, that's also 8. Notice that this is not an arrow. If this had been an arrow, then there would be no global maximum, because that would mean the graph would go up forever. If there had been an arrow right here, that was hard to say. If there had been an arrow right here, that would mean the graph went down forever and there would be no global minimum. Number 14, global minimum. The lowest point on the graph is right here. All right, it's just a dot, so this counts. It stops right here. So we have a global minimum of -2 at x equals -3. The highest point on this graph is right here. So we have a global maximum of 2 at x equals -1. New directions. For each of the following, determine if the given polynomial must have a global minimum, global maximum, or neither. Explain your reasoning. Quick side lesson. You can tell the end behavior of a polynomial by looking at the degree and the sign of the leading coefficient. The end behavior of a polynomial with even degree is the same on both sides. So it's either rising on both sides or falling on both sides. You will know which it is based on the sign of the leading coefficient. If the leading coefficient is positive, then it's rising on both sides. If it's negative, then the end behavior is falling on both sides. For odd degree polynomials, each side has opposite end behavior. So either it's falling on the left and rising on the right, or it's rising on the left and falling on the right. You can tell which one it is by looking at the sign of the leading coefficient. If the leading coefficient is positive, it's going to be rising on the right. If the leading coefficient is negative, it's going to be falling on the right. For number 15, focus on the leading term x to the 4th power. Because the leading coefficient is positive and we have an even degree 4, we know the end behavior is going to be like this. We say f of x must have a global max because the leading coefficient is positive and the degree is even. For number 16, the leading term of y has a negative leading coefficient and odd degree, degree 3. Therefore, we know that this is going to have end behavior that is rising on the left and falling on the right. Therefore, there is no absolute max, nor is there an absolute min. I started to say y has neither global max nor global min because the leading coefficient is negative and the degree is odd. But the fact that the leading coefficient is negative doesn't really matter. If the leading coefficient had been positive, the curve would have this type of end behavior, and still there would be no global min nor global max. We should say y has neither global max nor global min because the degree is odd. Number 17, looking at the leading term of g of x, we see that the leading coefficient is negative and the degree is even. That means the end behavior is going to be falling on both sides like this. That means there will be a global max somewhere, and there will not be a global min. So g of x must have a global max because the leading coefficient is negative and the degree is even. For the following polynomial graphs, determine any x values where the function has a point of inflection. A point of inflection is where the graph changes from concave up to concave down, or from concave down to concave up. For number 18, from left to right, the graph starts off concave down, then it switches to concave up in the middle, and then it finishes concave down again. That means we have a point of inflection that is about here, and I'm estimating a little bit, but I'm going to say we have a point of inflection about here. So I'm going to say we have points of inflection at x equals -2 and x equals 1. For number 19, the graph begins concave up, in the middle it's concave down, and then it finishes concave up again. So I estimate that we have a point of inflection about here, and another one about here. So we have a point of inflection at about x equals -2 and x equals +2. Sketch a polynomial function on the axes provided that has the following properties and the domain -infinity to +infinity. For number 20, we want f of x to have 2 points of inflection, but there needs to be one absolute max and no absolute min. So I'm going to focus on the second part first. If we want one absolute max and no absolute min, that means the overall outline of this thing has to be something like this. So the way I have it drawn right now, we have one absolute max and no absolute min. It goes down forever. I did throw one point of inflection in here, or did I throw in two? I wasn't even thinking about it that closely, but I think I nailed it, because the graph does start off concave down, and then at some point it becomes concave up in this area right here. So that means somewhere in here, maybe about here, there is a point of inflection. But then it becomes concave down again later. It's hard to pinpoint exactly where that might be, but you know, like somewhere in here. For number 21, we want g of x to have one local maximum, two global minima, and 2 points of inflection. So let's see, if we want two global minima, that means it has to hit the same low point twice. So I think I will use the x-axis as a guide. So if I do something like this, and I bounce off of this bad boy, and then I come and I bounce again, let's see what we've got so far. You can see that I have two global minima. All right, to be the global minimum, it has to be the same low in two different places. So we have two global minima. We do have one local maximum right here, so I accomplished that. How about these points of inflection? 2 points of inflection. So let's see, we went from concave up to concave down. So there's going to be a point of inflection in here somewhere. And then we went from concave down to concave up. So there's going to be another point of inflection somewhere in here. So that's it. For 22, we want m of x to have one point of inflection, no relative extrema, and no absolute extrema. Okay, so I'm picturing a cubic graph that just sort of does a nice wave. Okay, so you can see that that's concave down so far, and all of a sudden, oh, concave up for the rest. So by drawing it this way, you can see that I have one point of inflection, and there are no relative extrema anywhere, and there are no absolute extrema anywhere. For number 23, we want k of x to have one absolute extremum, no points of inflection, and one local extremum. Well, this will be pretty easy if we just draw your classic parabola type shape. This fits all the criteria. It has one absolute extremum, right? Meaning we have one absolute min. There are no points of inflection. It's concave up the entire time. It also has one local extremum because this vertex at the bottom is both the absolute min and it is also a local minimum. Hey guys, don't forget to like and subscribe, but also if you found this video helpful, there's a lot more where that came from. You can click the upper link, which will take you to the whole unit playlist, or you can click the lower link, which will take you to the next video in the playlist. See you there.